All right, guys. Welcome back to Condensed Matter. I heard you guys had a good time in tutorial yesterday. Today what I'm going to do is talk a little bit more about the reciprocal lattice and identify the reciprocal lattice vectors with an important physical object. And the way to think of the importance of the reciprocal lattice and the importance of talking in Fourier space or dealing in Fourier space becomes evident if we think of a scattering experiment where we have a plane wave, some electromagnetic wave, like maybe an X-ray, or even a plane wave of something like neutrons, incident on a Bravais lattice. So you have some plane wave here, incident on some lattice, and that plane wave can be described by a position and a wave vector. And I haven't put the time dependence in, but we'll deal with explicit time dependence in a moment. So now for a general wave vector k of this incident plane wave, it in general won't have the periodicity of the lattice. Okay, so but special wave vectors will. Okay, so you can tune your wave vector, you can tune the momentum of the incident plane wave in this scattering experiment, this thought experiment, and capture the periodicity of the lattice. So the set of these special wave vectors So the set of all wave vectors k that result in plane waves with a periodicity of the lattice, ICE, are exactly the reciprocal lattice vectors. Which we were calling G in the last lecture. So this language of momentum space and wave vectors is the language that we're going to use from now on to describe the reciprocal lattice vector and to solve things in momentum space. And the reason this language is used is because the atomic structure or the crystalline structure of atomic solids is in a very practical way determined via these types of scattering experiments. X-ray scattering for crystal structures of solids, neutron scattering for magnetic structures or electronic structures, and so on. So we're not going to explicitly talk about Bragg conditions for scattering and so on in this class. You can read your books in order to see a little bit more about this stuff. But we're going to use this language of momentum space and wave vector when we talk about the reciprocal lattice. Okay, so you guys calculated some reciprocal lattice vectors yesterday, so just a quick review. The The form of the reciprocal lattice vectors is easiest seen by doing examples. And the simplest example is the 1D lattice. And a 1D lattice has there's one Bravais lattice in one dimension. And if I label the spacing between atoms or electrons or magnetic moments or whatever with A, then using your prescription from yesterday, the reciprocal lattice vectors, okay, so my primitive lattice vector in real space is just A1 equals A times, say, the unit vector x. Then the reciprocal lattice vector is simply 2 pi over A times a vector in the x direction. This is the most boring example you can think of. So B is this vector here. There's only one of them, B1. Okay. However, if we build the unit cell of the reciprocal lattice, it has a special name. If we choose, this Wigner-Seitz cell. And so to build that cell, remember, just like we did for the real lattice, I showed an example of the square lattice and the triangular lattice yesterday. So let me cut the reciprocal lattice by picking an origin, say, and cutting halfway between the next atom. So that space there, which goes from, I'm going to label it now with a wave vector k, from minus pi by a. Right? So the total length of the vector is 2 pi by a. This is my origin at 0. Here's k equals pi by a. This unit cell here has a special name called the first Brouillon zone. I'm not from the French-speaking part of Canada, so I'm just going to call this the BZ, or the BZ. And the first Brouillon zone refers to the fact that it's basically the closest way that you can make these cuts, and then you can make other higher order cuts, if you will, and get the second and third Brouillon zone. But we're not going to talk about these in this class. So the Brouillon zone is going to play a special role in our analysis of excitations in these lattice systems, which I'm going to talk about today. Okay? So you can see how the form of this vector B, this reciprocal lattice vector in one dimension, satisfies the condition for reciprocal lattices that we talked about last time. You can extend this to 3 dimensions. So let's say 3D simple cubic. Where A1, A2, and A3 have all the same length A, right? So very simply, length A along each of the unit vectors, x, y, and z. So you can guess what the reciprocal lattice vectors are. the volume of that Brouillon zone, that, the unit cell of that reciprocal lattice, comes into play whenever you take the continuum limit in K space, in momentum space. And we'll do this today. But remember what you calculated yesterday, the volume of this thing. The volume of the Brouillon zone, if you will, which is just B1 cross B2 dot B3. Becomes simple in this case because each one of these things is just, it's like multiplying 3 sides of a cube. So in each direction, the Brouillon zone extends from minus pi over a to pi by a in x, y, and z. Where I is x, y, or z. Okay, so just a little bit of review, a little bit of extension from what we talked about yesterday. What I want to do for most of the class today is talk about excitations in a lattice system. And now I'm just talking about excitations of the lattice itself. Okay, so if I have a crystal, I said it's ground state, the vacuum state, has this broken symmetry state. Broken symmetry state has these broken translational and point group symmetries, all these space groups that I didn't really talk about. So excitations, especially quantum mechanical excitations, become interesting when we're dealing with that vacuum state. But also in this class, you're going to deal with periodic systems where you might have electrons, or you might have bosons, or some more complicated sort of atomic species sitting on a lattice. And then you'll be solving for properties of the wave function. Okay, so these are two kind of different things. Imagine I want to know somehow the electronic behavior of, the conduction band of a metal in some elemental solid, and there's ions sitting at the position of a lattice. Okay, this lattice here, whatever lattice, simple cubic, whatever it is. The wave function of those electrons takes a special form. So even before even beyond talking about the lattice itself, the wave function of the species, whatever quantum mechanical species that sits on that lattice, takes a special form. And so I want to talk a bit about that. Because what we're doing in the end is solving, the Schrodinger equation for many electron system, if you will, that sits in the background of maybe an ionic crystal or something like that. And this is part and parcel of how we solve these condensed matter systems in general. So electronic states in a periodic crystal lattice are special. There's some considerable simplification that we can make on these electronic states. And basically what I'm doing is warming you up for what Xiaogan and Anusha are going to tell you in the second and third week. And one thing you'll have to know is the form of the wave function in a periodic potential that could be formed by this lattice, okay? So that would be one step of an approximation from this microscopic Schrodinger equation for all the ions and all the electrons with their kinetic energies interacting with a potential energy. it's a very, reasonable assumption to make in some sort of, say, crystalline metal that the electrons just see a periodic potential due to the ions sitting on a crystal lattice. Okay? And I'm talking about just looking at the solutions to a Schrodinger equation. Which might be the time-independent Schrodinger equation for a system of electrons, where there's a potential V, and that potential could be periodic. Now, you all know the solution to the Schrodinger equation for a particle in a single well. So where the potential is a hard-walled potential, and it's 0 inside the box, right? So you can label the wave functions with this wave vector k. So we've already seen this idea in quantum mechanics, right? And the energies depend only on k. So it's like the kinetic energy, like p squared over 2m. I better square it, right? Which gives this k the name momentum, right? It is the momentum. And it also has definite values that satisfy, the boundary conditions, if you will. So this is just like a single particle in a box. And you might imagine that this periodic potential is just like a bunch of coupled particles in a box. Right? So maybe there's an ion sitting on a lattice that has this periodicity. And these might not be infinite. They could be coupled in some way. Whatever. Oh, I want to make them fully periodic. And this could be my model for my potential, my V of x, in the presence of this lattice system. Okay? So crystal lattice, in some approximation, is like a coupled set of these particles in a box. And for this periodic potential, the solutions to the wave equation, the time-independent Schrodinger equation, have a special form. And that form is psi of k is some function, some periodic function, uk of r, times a phase factor that's just e to the I k dot r. Okay? And this u of k, this block function, has the periodicity of the underlying lattice, say. Okay, so this is called Bloch's theorem. The eigenfunctions of the time-independent Schrodinger equation for any periodic potential, doesn't really matter what it looks like. It could be a bunch of these coupled boxes, or it could be something much more complicated due to the underlying lattice. Okay, so the form of that the eigenfunctions are the product of a plane wave, this thing here, times what's called a block function, a periodic function. So plane wave multiplied by okay, so this is a very general result, this Bloch's theorem. And anytime you're solving any sort of electronic structure or anything that has to do with a periodic potential, you can invoke this Bloch theorem. So in the interest of time, I'm just going to give sort of a limited proof or just an example of how this works in a one-dimensional case. And you have to be a little bit more general than what I'm going to write on the board. You have to be more careful because you can have degeneracies and you can have higher dimensions and stuff like that. But I just want to illustrate this. In 1D, just so you get an intuitive feel for this Bloch's theorem. I'll say non-degenerate.
Those cases must satisfy an equation. We're just assuming that the dispersion relation of the electron is h bar per case per square.
Well, yeah. So that's generally a general tough question, depending on precisely the form of the potential. Those k's have some equation that they have to satisfy. Yeah. So that's just kind of intuitively, this is what you might expect if you're coupling a bunch of 1D particles in a box. But in general, you have to solve that's kind of what you're looking for. You're solving that problem. You're not necessarily looking for that Bloch function. You're looking for restrictions on the wave vector k. So this will become a little more maybe transparent when I do some examples. So in 1D, we can find these restrictions on k. So let's just look at a 1D lattice. There's n atoms, or n lattice points. The length of the 1D lattice is n times the lattice spacing a, whatever, 10 angstroms, whatever it is. That's the length scale of the problem, is that a. And let's put periodic boundary conditions so that this lattice is a ring. Okay? And so the potential is some v of x, depending on what's sitting on that lattice. But it has a symmetry such that if I move over by some number of lattice spacings, call it S, then that thing has a certain periodicity. Okay, so Vx is Vx plus SA, where S is an integer. Okay, so now we can look for solutions, basically by symmetry. To the time-independent Schrodinger equation that looks something like, if I move over by a lattice spacing, I'm going to get some factor, call it C, in front of my weight function. C is some constant. Now I can use this solution, I'm making a trial solution, and I can look at what happens if I go once around the ring. So if I translate over by n discrete hops of size A, and you can see quite simply that when I have the wave function x plus NA, I'll just get C times the wave function at position x. But I've applied this transformation n times. So I have some C to the n. But also the wave function has to be single valued. So right away, you can solve for the conditions on that C. It must be one of the n roots of unity, if you will, right? So C to the n must be 1. So C. So I can label it with this S, where S is an integer. And then my wave function has this factor in front of it.
Is that n different from the length n?
No, I've gone once around the ring.
Okay.
Right? So when I go once around the ring, it's not that my wave function has to be exactly the same. That's the point. It's single valued.
Why should we believe that when you go one lattice spacing, you multiply your wave function by a constant?
So that's just the form of the solution that we're trying.
Oh, okay.
And so I'm saying this isn't a proof. So if I try that form of the wave function, it's self-consistent. Now if I go less than one lattice spacing, right, so this constant factor has to be out front. But if I go less than one lattice spacing, then I have to generalize this. So then the full wave function has to be something like, some other function, just like your block function. Then e to the I, let's see, 2 pi. Right, so I have to account for a finite, or a different x here, so it'd be n over a, right. So that motivates that form of the general wave function. Does that make more sense? So if your system's fully periodic, okay, so your system's fully periodic somehow, you expect your wave function of some symmetry under that period. That is Bloch's theorem in some sense. So I've just assumed it here, and I'm showing that it's self-consistent. Now if I go all the way around the periodic system, the wave function has to be identically equal to itself, because it can only be single valued. So that gives me this restriction on any phase factor out in front, any phase that's accumulating. So here's that phase for a general x, and I still have to have some function that's periodic.
Does the Bloch theorem still work if we don't have the periodic boundary condition, say infinite max?
So yes, the answer is yes. I mean, if you have a macroscopic crystal, like a very large size crystal that has, finite boundaries, in effect, you're dealing with the same periodic system. So in practice, Bloch's theorem in the center of that crystal is the same form here. This might not look very useful right now. It's just motivating the form of this phase factor in some sense. And this ux has to have the periodicity of the lattice.
You don't really assume that. I mean, that's the only thing you can have, right?
This needs to have the periodicity of the lattice.
I think the argument behind that part is to say that translation operator commute the Hamiltonian, so you can find a common eigenbasis, and then you find the eigenvalue of the translation operator.
Say it again.
I mean, did you say you have to assume this form? of them?
Well, I'm just using this as a trial form, but this is the only form it can be, right?
Yeah, because it has to be eigenstate of the translation operator.
That's right, yeah. I mean, it's an illustration, it's not a proof, but I mean, it's the only case you can have, essentially. Okay, so maybe it's not that intuitive, but now essentially this K that occurs in Bloch's theorem, I motivated it as a momentum, and it is a type of momentum, right? And the wave function inside a crystal can have a momentum associated with that K, but it's not a real momentum. It's not like if you excite the crystal somehow, that crystal starts moving with a real momentum, right? So this is a crystal momentum, it's called. And it enters, it enters in the conservation laws that govern all the processes in the crystal, inside the crystal in and of itself. So you're considering this crystal as a vacuum state. And everything that goes on inside of that crystal, any excitations out of that vacuum that have momentum, right, that have some momentum, it's crystal momentum. It's not the object itself moving. Right? You don't do an experiment where you thermally excite your crystal and starts get some finite momentum and blast across a lab or something like that, right? So this is called crystal momentum, just to distinguish it from real momentum. Okay, so anytime these K's or K times X comes out in this phase factor, just keep that in mind. So we're going to use this concept of plane waves and crystal momentum in this lecture, and you're going to use it again when you talk about band structure. I mean, there's regions in solution space where these Bloch functions don't exist, and these are important in terms of bands. So forbidden regions, just keep this in mind if you see them in the future. These forbidden regions are what's responsible for bands. So this is the prerequisite for having insulators and conductors. So when you start talking about sort of band descriptions of electrons with Shaugen or Nusha, the existence of the bands has to do with this form of these Bloch solutions. So just keep that in mind. And in general, these are very simplified wave functions, although they might not look like it. So these Bloch functions. So of quasi-particle excitations in and out of these bands. So I'm trying to motivate condensed matter as being, a set of vacuum states dictated by a broken symmetry, excitations out of these vacuum states, and the simplest ones that you'll encounter are the quasi-particle excitations that occur in electronic systems that have a certain band structure. And all of that is a consequence of this Bloch wave function. Question? No, you're just waving. So, yep.
Solution? Is it boundary conditioning?
No, it's just destructive interference. Say it's one way to think about it. So there's destructive interference in the wave that lead to regions that are forbidden. That'll lead to gaps between, conduction and electron bands, and wherever the Fermi level lies. Well, you guys will see this next week. So you might see this Bloch's theorem again, but I suspect you won't. That's why I did it now. So when you need to use it next week, at least you've seen it once. So again, this is tied to the underlying periodicity and the assumption in condensed matter is that periodicity comes from a lattice. So you've cooled down some system enough that it's crystallized into a lattice. And the electron wave functions of whatever's existing in that lattice have this sort of fundamental form.
This crystal momentum you're talking about is usually restricted to the first billion?
Bronze zone, yeah. So we'll talk about that now again. Yeah. So the reason is, of course, if you have a n-site system, right, your reciprocal lattice vectors, I mean, there's only n of them. And so you have n of those vectors which are defined within your Brouillon zone. We'll look at that more now. So what I want to talk about now is not the electronic wave functions that might be sitting on this lattice and the form of them, but the actual excitations of the lattice itself. Okay, that's an important distinction. And so these fundamental excitations, because of this idea that we have crystal momenta, say, we'll fundamentally take the form of a wave, and that wave can be classical or quantum mechanical. And in the quantum mechanical case, these are elementary excitations called phonons, which are bosonic in nature. So that's what we're working towards now. I'm going to say classical and quantum waves 1, because I'm going to talk about waves in magnetic media also. So this is lattice vibrations. And the quantized version of lattice vibrations, which are called phonons. So these become important because, the thermodynamic signatures of lattice vibrations, so say you have a crystal lattice and you're cooling this thing down or warming it up, the thermodynamic consequences of these lattice vibrations can compete with, say, the thermodynamic signatures of some electronic state or some insulating state that we're searching for. And it's very difficult to decouple lattice vibrations and sort of electronic wave functions. And in some cases, they couple so strongly, like in BCS superconductors, that they lead to new quantum states. And just an interesting note, a lot of people work on experiments in cold atomic systems these days where your periodic potential isn't produced by an underlying lattice, but your periodic potential is produced by standing waves of lasers. So you can take lasers, produce standing waves, and then the potential from that laser is like a periodic well that you can dump atoms in. So these cold atomic systems mimic in a lot of ways the physics of condensed matter systems, with a very important exception is that they typically don't have phonons in them. So they are, in some sense, cleaner. This is some, in some sense, it's a very fundamental quantum excitation that I'm going to talk about now. But in another real sense, it complicates experimental signatures. And if we step outside of the traditional definition of condensed matter and consider things like cold atomic systems, much of this formalism still applies, but what we don't see is phonons. Okay, so what are we doing here? So okay, so let's look at elementary excitations. And we should be thinking of wave motion. for example, sound waves macroscopically. So sound waves come from some sort of excitation in a system. But instead of looking at macroscopic wave motion, let's look at the microscopic origins. In a crystalline system. Okay? And to describe this wave motion, we're going to basically derive the frequency or the wavelength, the frequency energy relationships given simple crystal structures, periodic crystal structures. So to start, we're just going to talk about Bravais lattices. So there's some atom, kind of some mass, sitting on a crystal lattice, one atom per unit cell. And really, I'm only going to think typically about simple hypercubes, so 1D, 2D square, and 3D cubic lattices. And remember, these things have a vector, a position vector. And I want to take this vector and I want to give it a little bit of a push. So let me call it R naught at equilibrium. So that the atom in my unit cell has some displacement vector u. Okay. So it's deviation from equilibrium. And we're always going to assume that the magnitude of u is small. So what's that? U over A, say, is less than 1. Okay, so let's think of classical dynamics. And we'll move on to the quantum case later. Let's derive the equations of motion for atoms under some assumption of the force between them. And in general, solving F equals ma for all these particles can be quite difficult. But we're going to simplify things down to some sort of high symmetry cases. And let's imagine that planes of atoms are moving in these systems. So 3D cubic systems where planes. Okay, so whole planes of the atoms moving. So there's an equilibrium position. So maybe I have one plane of a 3D crystal. And I can label each one of these planes. So this is maybe S minus 2, S minus 1, S plus 1. So that's my perfect square lattice. And now I'm going to displace a whole plane of atoms. So maybe at S, they're not displaced. They sit right on their positions. But maybe at S plus 1, they're slightly displaced. And maybe S minus 1, they're slightly displaced in some way. S minus 2, maybe they're pushed farther off. Okay, so the displacement at each plane is U of S. So this is U of S plus 1. Say. Okay, do you see what I mean? So these are my planes here. And the atoms are displaced by some amount, which is the white. Okay, so we need to have some sort of an equation of motion that depends on the interaction between the planes. Okay? So note that if I had a simple 1D crystal, my description's still valid. I could just cut out this one-dimensional line and say, I'm forming some sort of regular displacement. So we need an assumption on the interactions. And in general, this is quite difficult. So you can imagine that, depending on what type of atom you put on these white dots there in this crystal, the interaction could be quite complicated. So it could be dominated by its interaction with its neighbor, but it also could have some long-range dipole moment, for example. So if I put a dipolar moment on this atom here, then it's no longer just it's no longer just nearest neighbor interactions. It could be very long range, all sorts of spin-space coupling. And in general, people deal with this stuff all the time. They do the derivations like we're going to do today for very complicated interactions. But since it's our first time, let's just assume the simplest. Which is nearest neighbor. And nearest neighbor interactions just mean that each atom, whatever it is, has some interaction that only ties it to its neighbor. So it could be its neighbor in any of the planes, right? But in principle, we expect this to be the equilibrium distance here. So the only interaction that matters in our force equation is the interaction along this displaced direction, if you will. So let me write the force on a plane with some force constant, which is the same for each direction of neighbor. My force constant is C. And see, I have the difference in positions between U of S and U S plus 1 and U of S and U of S minus 1 here. And I've assumed a linear restoring force. So this is like a harmonic approximation. And just like you do in undergrad classical mechanics, you can assume that this is the first sort of non-trivial element of the Taylor expansion. Right? So if you Taylor expand, you have x squared in the potential, then all the higher x3, which is usually gone by symmetry, x4, and so on. Right? So this is like the x squared element of the potential, which gives you the x, f equals kx.
For one direction always?
It's always a restoring force, right? So, yeah, I mean, you have to treat these u's as vectors, but so it should always be a restoring force, right? So, if this is displaced outwards, my force is that way, right? And if this is displaced outward, my force is that way. So. Questions?
Are you ignoring like a lattice spacing term that would just be a constant?
So this is the displacement of each plane. So there is a lattice spacing here, right? That's A. Between, A is the distance between the equilibrium positions. So if everything's sitting at the equilibrium position, there's no force. Okay.
Do the two C's necessarily have to be the same?
No, they don't. I've just done it like that so that it's easier to solve. But C's could depend on all sorts of things, like directions or,
So in general, it's some tensor object.
Yeah, so you can have like a C that's a certain value for nearest neighbors. Then you could have C that's a different value for next nearest neighbors in that plane, out of that plane, right? So that interaction can be like very, very complicated, actually. So it's just like the simplest case. So that's the force on one atom, by the way. In general, you have a set of highly coupled equations. Everything's coupled together. So you displace one atom, it affects all the atoms around it, right? That pulls that atom out of its equilibrium position, affects all the atoms around it. So all these force equations are coupled, and this is just the force on one. So what we're going to do is decouple these equations and solve them. That's the essential lesson for today. So let's write the equation of motion. Which will lead us to a form. So let's say the m is the mass of all the atoms. Okay, so let's say it's F equals ma. Okay, so I have C, I'm just taking that force equation here. S plus 1, S minus 1, minus 2 US. Okay. And now we're going to look for solutions of the form of a expansion in running waves. Okay, so what I mean by that is I'm going to look for something that's US, right? So this can be 1D, but I'm just going to write it in 3D in general. Because I've been just dealing with planes, I'm effectively doing a one-dimensional force equation. But this can be generalized to 3 dimensions, no problem. And I'm going to assume an equation of this form. Okay, so this is just like I've been talking about. It's like a plane wave part here with a time dependence. And that time dependence will explicitly, bring out my frequency here and then cancel after that. So this is a normal mode analysis. Which is really just an expansion of the solution in running waves. And you can imagine it as a trial solution that we're going to write down and plug into our force equations. But again, it's the only form of the solution that decouples the equations. And it can do that because of the periodic symmetry, because of the translational symmetry.
What is the R of this?
That's the position of the, so it's like the generalization of U. It's just the position, right? It's K dot, K dot R. Don't worry, I'm going to write, this is just like the general form. I'm going to write the specific form right now. So I'm only really writing one-dimensional equations here, but I wrote something in 3 dimensions here. And you actually have to be careful that, there's different modes of motion in higher dimensions. So what I've drawn up here, if I imagine a plane wave solution with a wave vector k in this direction, the direction of the displacement's in the same direction as that k vector. But in a higher dimensional crystal, anything higher than 1 dimensions, I can also have displacements in transverse directions. So this is a longitudinal. So a transverse wave would look different. So let me take my equilibrium positions. Okay, so these orange things are my equilibrium positions. And I can have a plane that's displaced. So I can have one that's not displaced, say, my plane S. But I could also displace upwards on S plus 1. Well, that displacement is supposed to be much less than A, so I'm drawing it in some exaggerated way. But what I have here is some sort of wave, right? I can imagine that thing has some long wavelength. So I can also have, in this nomenclature, a wave vector k where the displacements are transverse. So this is a transverse wave. So these are called modes. In a 3-dimensional crystal, I have 1 longitudinal and 2 transverse modes. Okay, so what are these modes? Let's go back to the 1D problem and solve this properly. Okay, so in the 1D equation, which is just representing the planes, I have a trial solution that I'm going to plug in. And doing so, say I have a second derivative, so that'll pull out an omega squared in the front. So I just have a difference equation, just a difference of sort of amplitudes. Okay, so u is just, r is just the general form of my displacement vector u. And my time dependence now, my explicit time dependence in that equation, that e to the minus I omega t, won't contribute past giving me this omega squared here. And that u out in front, right, whatever that constant is parameterizing my wave function, also cancels. Okay, so using the spatial part for u of s plus minus 1, all right, so this will be some u, some e to the I omega t. These things are going to cancel in this equation. What I have left is I, what would I call it? So it's sk A, right? A is my equilibrium lattice spacing. Then E is going to be, so if I have plus or minus 1, so this will be plus or minus here, 1. So I, K, A. So that's my solution for u s plus 1 and s minus 1. So I plug that in. And again, k is a wave vector. So this gives me something that depends on the wave vector. Let's see. So u s plus 1. I canceled the time dependence. Oh, I could have canceled the u, but I left it in. Doesn't matter. So let me simplify it then. So this cancels, this cancels. So I have omega left. So let me say m omega squared. So the only thing I have left here is e to the plus I, ka, plus e to the minus I, ka, and this exponential cancels. Okay, so my solution works. It's giving me something that has an explicit k dependence in it, and also has the omega, the h bar omega, relating it to the energy. Okay, so let me just use the definition of cosine Ka in terms of exponentials. And that'll give me something in terms of a cosine, or it's 1 minus cos. So I can write that in terms of sine with a trig identity. I think this is the one I want. So that'll be omega squared. So let's see, there's a 2, so it's 4. Yeah, this makes sense. Sine. Or I can take the square root of both sides. So say absolute value. So the introduction of this normal mode analysis decouples the equations into just a simple sum over these k's. Okay? So previously we had all these f of s, all of these spatial indices are coupled together in some complicated way. Now we're going to have a nice solution that's decoupled, and it's just a sum over all of these modes. So that's the essential power of this sort of normal mode analysis. And furthermore, we can whittle this down to a very nice, sine function, essentially. And that sine function, okay, so it's an absolute value. So if I can plot the omega, the angular frequency, if you will, versus k, and that thing's called my dispersion relation. And it's a measure of how the energy depends on those wave vectors k. Okay, so how does this look? I can draw it here. So I have something that's like, let me draw my axis Ka. Okay. So the amplitude is 4c over m, right? So then it goes from 1 down to 0 as a function of Ka, and like the absolute value of a sine wave. Something like that, right? And as you can see, this thing's periodic, and it repeats, right? So sine is 0 at k equals 0, or k equals 0. And when Ka is pi, right, or minus pi, that periodicity repeats. And that's exactly the first Brougham zone that we calculated at the start of class. So it's the first Brougham zone for this simple cubic type system.
You did this just in one dimension, right? By considering two dimensions, then that equation becomes a matrix equation, and I can have different dispersion relations.
Right. So yeah. So in higher dimensions, you basically have to label, your wave vector. So there's 3n wave vectors then. Okay. There's one wave vector for every particle in each of the directions that it can oscillate. So those equations. So now instead of just having like n equations in one dimension, you have 3n equations in higher dimensions. So I'll mention that, but yeah, you're right. So you have to take into account the fact that all of these modes and all of these dimensions are decoupled in this mode analysis. So you have to label your omega by all possible values. Okay, so this is just sort of a one-dimensional picture, but let's just look a little more closely at its behavior in the first Brougham zone. So again, it repeats. So you only have to consider, k is k between minus pi by a to pi by a. And in particular for small k, if we just expand that sign out, we're going to get something like omega goes to some constant, you can call it v times k. Right, so there's a linear regime down here. And that'll become important, I guess, tomorrow when we talk about thermodynamics of these lattice waves. And so this is very much like sound waves. So it's a long wavelength behavior is like a sound wave. It's when you have a small k. And then the velocity of that wave is something, whatever, c a squared, something like that. I think that 2 cancels. And so this is like the continuum approximation. Okay? So that's like the long wave. That's what you expect in the long wavelength behavior. So if I move up this curve, I also have a region here where, where I'm close to Ka equals pi. I just have u plus or minus 1. These things are just standing waves. Okay, so the waves move neither to the left or to the right. So they're like standing waves in your system. So that's just a very simple decoupling, if you will, of all of Newton's, all of the F equals ma, which depend on the differences between all of these atoms, into something that only depends on the wave vectors k. And I've really just done a treatment in one dimension. Right? So in higher dimensions, again, you have more modes, if you will. And you have to take into account these modes when you sum over k. So I'm leaving this polarization label off, but this basically is a direction. So I've illustrated two there. One's longitudinal, one's transverse. There's two transverse directions. So if I have a wave vector, let's say x, y, and z. I have a longitudinal mode, or longitudinal polarization for each n this way. Right, that's atoms being displaced in this direction, and they can be displaced in these other directions too. So it's one longitudinal. Did I write this? So 3n total. Don't worry, you're going to get lots of practice with this. So this is very simple. This is a sort of a one-dimensional solution that has been based on just a Bravais lattice, a simple cubic lattice. And this is the dispersion relation here. And things don't get too much more interesting until we look at more than one atom per unit cell. And this is what you're going to do in your tutorial. Diatomic length. Oh, and I see that I used different notation than Dennis. So let me just make a note of this now. What if I have 2 atoms per unit cell? Well, the dispersion relation will change. So in my notes, I have a set of labels, but I think I'll write a dictionary between these in your tutorial. Okay, so I have a one-dimensional lattice with a basis. Okay, so this is my lattice point, say. Then I have 2 atoms in the basis, so 2 atoms in the unit cell. And those atoms can have different mass, so say M1 and M2. Okay. The lattice spacing is still A. And one of the bases is at vector 0, and one's at vector 1/2, in the x direction. And I'm going to label their positions u and v. All right, so this is us plus 1. This is v s plus 1. And the coupling constant, the spring constant c, so the force constant. So you're going to solve this in your tutorial. Just make a note. There, Dennis has used U1 and U2 instead of U and V, and he's used K instead of C. Okay, I think everything's pretty much the same besides that. So let me walk you through the setup of this problem. And you'll get practice completing all the steps this afternoon. So what we want to do is write down the force equations, the equation of motion. For this case, when we have these two atoms. So assuming nearest neighbor harmonic interactions. Then I'll get two equations. One for U and one for V. So the top one's U, this one's V. Okay, and the U is dependent on its neighboring V's. So I just have to keep that in mind. So I'm using the same constant here. And I'll use the same form of the equation as I wrote over there. So it'll be V. So if I'm at US, so this will be VS. VS plus 1. All right, say VS minus VS minus 1. And in this equation for V, the US plus 1, US minus 2V. Okay, and we have as many equations coupled together as we have atoms in the system. So we're going to decouple these equations by essentially moving to Fourier space. We can use that normal mode analysis. So US is U e to the I S K A e to the minus I omega t, and oops, V will be D e to the I K I S K A. Okay, so the setup is exactly the same, and each atom only interacts with its nearest neighbor. But the atoms in the two different sublattices, if you will, or the two different planes, this is one plane, this is another plane, they're coupled in these equations. Okay? And so what I do is I substitute in, these solutions into these equations. I'll get two equations. I think this one's minus here. That's 1. The other one will be minus omega squared m2 v. So that one's u. This one's v. It's cu. Minus 2 c v. Right?
Which ones are used? I think there's either you we mixed up somewhere or they look the same.
Oh, this is u here, right? Yeah, good catch. So this is the equation for v, and it's neighbored by u's. This is the equation for u, and it's neighbored by v's. Okay, so this is the same way you'll set up your question 1A of your tutorial. So now you have these coupled, you have a set of linear equations, right? And they, as any set, so these are homogeneous linear equations. So the determinant of the coefficients of u and v are the important object here. So I can't see over there, but I wrote it down. So it's 2c minus m1 omega squared. Okay, so that's the coefficient on the first equation of u. And then v will be the rest. And then in the second equation, the two coefficients are thus. That determinant has to equal 0. That's how you solve for omega. And the k-dependence of omega is the dispersion relation. Okay, so this is what you're solving in your tutorial. So it gives you a quadratic. And that quadratic has roots. I mean, you can see what it is. It's just this times this minus this times this. So you should get roots that you'll be solving for. And to check to see if you get the right answer, just examine a couple limits. So the first limit will be Ka less than 1. You're going to have some exponentials here. Okay, this will give you a cosine. Expand that cosine out. So you'll have a cosine Ka, 1 minus 1/2 K squared, A squared. Plug that in. And in that limit, you'll get 2 roots. Okay, and one of those roots is, so this is an omega 4 equation, omega to the 4th. So you get 2 roots in omega squared. So one will be looking like this, and one will look like this. And these are approximate. Okay, now Dennis is mad at me because I gave you an answer, but I wanted to illustrate a point here, is that the two roots that you'll get this afternoon have two very different functional forms. One depends, so omega depends linearly on the k vector, and one will not depend on that k vector. So unlike your dispersion here, okay, so that bottom solution is like the solution of your dispersion relation here near k equals 0, but the top one is very different. Okay, so this one's a lot like your acoustic branch because it has to do with the sound. You know, the dispersion looks like the sound equation. Omega equals velocity times k. But the other branch is a constant independent of k. So it occurs very high up somewhere in the dispersion relation.
The first solution that you have, if I take the limit where the masses are the same, shouldn't that omega go to 0?
Okay, well that's a tutorial problem. Yes, you will explore that. Yes,
that's the limit that you should receive. You should get the same solution. Okay. So you'll explore that. Don't worry. This afternoon. Let me just say, take another limit. So that's one limit. Ka is basically goes to 0, and the other, which will be Ka going to about plus or minus pi. You'll also get two solutions. Okay, which I'll call, which don't have a k dependence, so I don't have to call them anything. But they depend on the inverse masses. And so I can just draw the dispersion relation, omega versus k, for these two different cases. So when k is close to 0, I have something that's linearly dispersing. And then I have something that's a constant. And that constant's that thing, root 2c 1 over m1 plus 1 over m2, whatever. And at the edge of the Brouillon zone, okay, so when k is pi over a, I have two solutions. And it depends now on the masses, but I'll basically get something that's flattened off like this, something that looks like that. And this is one of the solutions. And this is for m1 greater than m2. So I've given you the answer. Now you have to derive it in your tutorial. But the point is that when you have a system with more than one atom per unit cell, you get branches in your dispersion relation. Okay, this is like your acoustic branch here, because it looks like sound waves. And this one's called your optical branch. And they behave differently. So in the long wavelength limit, your acoustic branch is just like I drew it. It's like atoms are being displaced. You know, both atoms in the basis are being, say, displaced forward and then backward at a long wavelength. Okay. In the optical branch, the atom on site, whatever you want to call it, A and B or 1 and 2, the atoms move in the opposite directions. Okay. So that's the sort of fundamental distinction between acoustic and optical. And this one where they move in the opposite directions, it's called optical because these ones typically scatter electromagnetic waves. And so these are responsible for most of the optical properties of solids. Okay. If you have a higher dimensional crystal, so if you have like p atoms per unit cell, I forget how this works. So it's p, it's 3, yeah, that's right. So it's 3p in the optical. Well, it's 3 in the optical and in the acoustic, and 3p minus 3 in the optical. So right, so your 3p modes are divided up like that. Okay, so in your tutorial, you'll actually derive this equation by looking at that, the determinant of that matrix, the coefficient. And you'll look at this case when m1 equals m2, try to recover that limit, right? This is basically what you're looking for. And then you have another problem that's linear chain with mth nearest neighbor interactions. Okay, so that's like the next most complicated sort of interaction that you could have in these types of systems. Any questions? So this is all I'm going to say about the classical theory of lattice vibrations. And we're going to start delving back into the quantum world in the next class, and we'll look at phonons and how they represent quantized lattice vibrations tomorrow. Okay, see you guys then.